One thing I always enjoy pointing out is that NP-Hardness is about Turing machines. It's about symbols and tapes and state transitions and moving heads. I mean, there are shortcuts to think about this, so they're basically equivalent in all the ways that we care about. But here's a formal implementation detail, so to speak, that kind of leaks out of the definition. The way that we normally specify problems, we say, oh, the input is a graph, for example, and then does this graph have a Hamiltonian cycle? What about the tape of my Turing machine, though? How is this graph represented? What is the alphabet of symbols, and how long is the description of this graph? Because we're supposed to give a runtime bound in terms of the input length. What is this length? And the answer is, we don't really care. We'll just give a bound in terms of the number of vertices or edges or whatever, and then we talk about something like reasonable encodings. To say that this Hamiltonian cycle problem over here is NP-complete is to say there exists a reasonable way to encode graphs into a Turing machine input tape such that the problem of recognizing Hamiltonian graphs is NP-complete. And for NP-completeness, we don't care about polynomial factors, so that's probably fine. Maybe we do an HSC matrix, but you have to be a little bit careful. Here's a question. What is a reasonable encoding for unbounded natural numbers? Maybe for the problem, given a number n, is it prime? This is not NP-complete. Well, probably not. There's a polynomial time algorithm, so that would be surprising. But polynomial in what? How do we encode the instance? How do we write n on the tape of a Turing machine? Well, I guess we write it in binary. That seems reasonable, and yeah, that is how you would do that. But then, in a certain number of symbols, I can encode an exponentially large number. The length of the instance is log n. So what you call a polynomial time algorithm for primality testing should be polynomial in log n. Simply trying all divisors sounds like linear time, but is actually exponential time in the length of the instance. And what this means is that if the input to your problem has numbers, you have to be a little bit careful about what the size of your instance actually is, because maybe there's an exponential difference there, and that might influence NP-hardness. This leads to the concept of strong and weak NP-hardness, as well as the concept of pseudo-polynomial time, which we might talk about some other time.